So linear space, your topic starting with linear space, normed space, first example. So 1.1 linear space. Linear space, another name is vector space. So E is over a field F is a linear space, means F may be R or C, that means the real number or the complex numbers. Over a field E is a linear space. So we are assuming that linear space means it's a vector space. First of all, it should be an abelian group. Second one, the scalar multiplication should satisfy four conditions. That is, C into V1 plus or alpha plus beta is equal to C alpha plus C beta, and C1 plus C2 of alpha is equal to C1 alpha C2 alpha. Then C1 C2 of alpha is equal to C1 of C2 alpha or C2 of C1 alpha. Then the last one, 1 into alpha is equal to alpha for every alpha belongs to your vector space V. So that is just your linear space or the vector space. So we are defining a vector space over a field F, and that F can be real number or the complex numbers. For the examples, we can take Rn, Cn, that means the n-tuple space of real numbers or the n-tuple space of complex numbers. The space of polynomials of degree less than 3. This we might have come across in your first sem linear algebra course. That is the space of polynomials of degree less than 3. So its basis contains the elements 1, x, x square, like that, of degree less than. So strictly less than means up to x square only it will come. Now C of closed level AB, which is not finite dimensional, that means the set of all functions, continuous functions from closed level AB, that we can define on closed level AB. That is your C of AB. Now in example 1, 2 are the finite dimensional spaces, but in example 3 we are dealt with an infinite dimensional space. So here is given the explanations. C of AB stands for the space of all continuous real valued complex valued functions on the interval closed level AB. So some basic notations. A map A from E1 to E2 between two linear spaces E1 and E2 is called linear if and only if for every x, y belongs to E1 and any two scalars a, b, we have the relation a of x plus by equal to a into a of x plus b into a of y. It is very familiar for you. In your linear algebra course in the first sem, you have studied what is a linear map. So here also we are having a vector space E1, or you can say the linear space E1 and a linear space E2. Then a map A from E1 to E2 is said to be linear if A of ax plus by is equal to A into A of x plus B into A of y. It should be taken care that the spaces E1 and E2 will be defined over the same field. So two important sets associated with a linear map is, one is kernel and another one is image set. So kernel of A is defined as set of all x belongs to E1 such that Ax is equal to 0. That means you are collecting those elements in your set, in your space E1 such that that will map to 0. Okay, we'll take those elements in your E1 that will map to 0. Now image we are denoting as Im of A, that is Ax such that x belongs to E1. That means you are collecting those images of all the elements of E1 and putting together in a set. It will be called image set. This we have proved that kernel of A and image of A are also linear spaces. That means we should prove that kernel of A and image of A both are vector spaces. That we have proved in your linear algebra course. Now let E1, E2 be linear spaces and A from E1 to E2 be a linear map. Then consider kernel of A. That's equal to set of all x belongs to even such that Ax is equal to 0. Now let x comma y belong to kernel of A. That means x is equal to 0 and ay is equal to 0. Now we want to prove that cx plus y belongs to our kernel. This is our usual method to prove as space is going to be a subspace of a vector space. That means you will take two elements and you find what is cx plus y. If that also belongs to the space, means you will say that it's a subspace. Now consider for some c belongs to f, a of cx plus y. If you are getting this also 0, means we may imply that cx plus y belongs to kernel. So a of cx plus y, that is equal to c into ax plus ay. That is again going to be 0 since a is linear. Now which implies cx plus y belongs to kernel of a. Now kernel of a is a subspace of E1. Similarly, we can prove image of a is also a subspace. That I am leaving here. Now we can note that if kernel of a is equal to 0, then a is one-to-one map. And a linear map A from E1 to E2 between two linear spaces E1 and E2 is called an isomorphism if kernel of A is equal to 0 and image of A is equal to E2. That is, in between two vector spaces or a linear spaces, we will say that a map is a isomorphism if first condition it should be 1, 1, second one on 2, and the third one is it should be linear. So a linear map from a linear space to a linear space is an isomorphism if it is 1, 1 and onto. For checking 1, 1, if you are checking its kernel and its kernel containing only the singleton 0, then we will say that the map is 1, 1. And further, if you are checking the image set and you are getting the entire set E2, that is the codomain, we will say that the range is equal to codomain, so our map is onto. Now if A is one-to-one and onto linear map, thus it is invertible and we denote it as A inverse. Now here is some examples of linear spaces. Consider a sequence AI, I is equal to 1 to infinity. This is the notation that we are following here. In some cases, it won't giving us I equal to 1 to infinity. It says that in the bracket we will write AI and we will write here from 1 to infinity. That means it's a sequence. So consider it is the notation we are using in your textbook. So consider a sequence AI such that AI equal to 0 for all I greater than n. So after a finite stage, you're getting every element of your sequence is zeros for some n belongs to n. Now consider a space S star consisting of the above stated sequence. Consider a space S star consisting of the above stated sequence. That means S star containing those sequences for that after a finite state, whatever the elements coming after the finite states all are going to be zeros consisting of the above stated sequence. Now this set of sequences is said to be a set of sequences with finite support. That means up to a finite thing it is non-zero, remaining is zeros. Now if xn and yn, we are taking the infinite tuple space, that is x1, x2, etc. and yn is equal to y1, y2, y3, etc. Now x and yn belongs to S star. That means after a finite state, whatever the elements coming for xn is 0 and whatever the elements coming yn is 0. Then define xn plus yn. You get x1 plus y1 first term, second term x2 plus y2, etc. Now what is cxn? Cxn is c into x1, c into x2, etc. Coordinate wise multiplication. Then S star with the above operation is a linear space. S star with the above operation is a linear space. We want to show that this is a vector space. Now the set of all sequences which converges to 0. First we have taken the sequences whose finite number of terms are non-zero, and now here considering the set of all sequences which converges to 0. Now we denote this as C0. The set, third one we are considering the set C of all convergent sequences. All convergent sequences we are to take, and let L infinity of all bounded sequences. We know that a sequence xn is said to be bounded if norm or mod of xn is less than m. Since we are taking your real or complex number, we should read it as mod of xn is less than m for every n. And fifth example, the set of all sequences S. Now from example 2, 3, 4 and 5 will again form a linear space with the same operation that we defined in your first element. That is, addition means coordinate wise addition, and scalar multiplication means you should multiply with the scalar to each and every element. So with respect to this 5 will, all the 5 will form linear spaces. Now actually we can compare this to, we know that the relation connecting convergent sequences and bounded sequences, and those two converging to zeros, like that. So how we can compare it? The relation. So the relation connecting this this means a sequence. This means the sequence having a finite number of terms non-zeros. This means the sequence converging to 0. So definitely this one contained in this. Now this means all the convergent sequences. So definitely it will contain those sequences which converges to 0. And what about this one? L infinity is the bounded one. So what is the connection between a convergent sequence and a bounded sequence? Bounded sequences are, no, it's not like that. Bounded sequences are not convergent because you can take 1 minus 1, 1 minus 1, 1 minus 1. It is a bounded sequence, but it won't converge. But the convergent sequence is bounded. And if this is a bounded sequence, it is the space of all sequences. So whether it's a bounded or unbounded, that will belongs to the sequence. So this is the inclusion relation. Now I have said that all bounded sequences are convergent. No, it's not the other way. All convergent sequences are bounded. So we will prove that here C is contained in L infinity since all convergent sequences are bounded. This you have done in your real analysis class. For like I'm dealing with only real numbers here, or I have put the modulus instead of modulus. I have put norm here. So now you read it as mod. That's enough since we are taking real number or complex number. So let xn converges to x for every epsilon greater than 0. There exists. Suppose you have got a sequence that converges to x. But then by the definition of convergence, for every epsilon greater than 0, there exists a natural number such that norm of or mod of xn minus x is less than epsilon for every n greater than or equal to n. Now we can take this epsilon to be as 1. So you take your epsilon value to be 1. Then mod of xn can be written as mod of xn minus x plus x. Now use the triangular inequality. That is less than or equal to mod xn minus x plus mod x. But xn minus x we have assumed as less than epsilon. So you will get this value as less than epsilon plus mod x. But we have assumed the epsilon value as 1, and this is equal to 1 plus mod x. Now we take the supremum of this mod x1, mod x2, mod x3, etc. mod xn minus 1 comma 1 plus mod x as your capital M. Now mod of xn is less than m for every n since m is going to be the supremum, which implies If this is the case, means we will say that the sequence is bounded. So all the convergent sequences are bounded. The other way is not true. I already said 1 minus 1, 1 minus 1. You can go for your own examples. So not 1. I may say counter examples, right? So not 1. A subset even of the linear space E is called a subspace of E if it is closely related to the linear operation in E. And we write E1 is contained in E2, or E1 is a subspace of E. See the notation? It is a just an arrow with a bend. See, like this. So in your textbook, it is given as, if this is the notation, means whatever you are having here, if I am having A here and if I am writing B here, so the meaning is A is a subspace of B. So this is the meaning. And when you say that this is a linear, one is linear space, E is a linear space, and E1 is a subspace of E, means E1 it should itself should be a linear space. So it's called E1 is a linear space. E is called a subspace of E. E1 of the linear space E is called a subspace of E if it is closely related to the linear operation in E. And second one, a set of vectors x1, x2, etc., xn is called linearly independent. This also we have studied. That is, we will say that sigma ai xi is equal to 0 implies all xi should be equal to 0, means we will say that it is linearly independent. So if there exists at least one ai such that ai not equal to 0, we will say that linearly dependent. Okay. Now we can see how it is dealing in your textbook. So the vectors x1, x2, etc., xn is called a linearly dependent set. I repeat, linearly dependent, we are saying. Linearly dependent set, and the vectors linearly dependent vectors if there exist numbers ai. See the notation ai. We will say that a1, a2, a3, etc., an. Instead of that, this is giving us a finite sequence ai, I is equal to 1 to n. Not all of them are 0, such that a1 x1 plus a2 x2 plus etc. plus an xn is equal to 0. Thus, see, not all of them are zeros, so at least one of them should be non-zero. So this is equal to a1 x1 plus a2 x2 plus etc. plus an xn equal to 0. Thus the vectors xi from I is running from 1 to n are called linearly independent if they are not linearly dependent. That is, sigma I is equal to 1 to n ai xi equal to 0 implies all ai must be equal to 0. Now, infinitely many vectors. When you're considering infinitely many vectors, then you will say that this set of vectors is linearly dependent or independent. So here's the definition. If vectors x1, x2, etc. are we are considering are linearly independent if for each k x1, x2, etc., xk are linearly independent. That means when you're considering from the infinite collection, when you're considering the finite collections each time, and you are getting that the finite collection is linearly independent, we will say that the infinite collection is linearly independent. Now third one, the linear span of a subset M of a linear space E. Linear span. The linear span of a subset M of a linear space E. This we can deal in two different ways. One way is that we should say that this is going to be the set of all linear combination of elements which contain inside your M. That means you take the elements from your subset M and go for all possible linear combination of those elements. So whatever you will get is going to be your span of M. So here is another definition. So a linear span of a subset M of a linear space E to be the intersection of all subspaces of E which containing M. So you take all those subspaces of E which contain M and take that collection and go for its intersection. You'll get the span of M. That is, span of M is equal to intersection over alpha E alpha, such that E alpha is a subspace of E and M is contained in E alpha. See how cunningly we have used that notation here. E alpha is a subspace of E. Or span of M is the set of all the finite linear combination of vectors from M. Okay, in both ways we can deal. Span of M means first of all you are taken as the set of all those subspaces which containing M and took its intersection. And the other way you have taken the all elements of M and the span of those elements, and the linear combination of all possibility of that elements, and whatever the set you are getting, that set is going to be the span of M. Now we are going for the first theorem on your session, theorem 1.1.2. So let xi from 1 to n is nothing but x1, x2, x3, etc. Okay, so sequence be a maximal set of linearly independent vectors in E. So what do you mean by maximal set of linearly independent vectors? It means that further extension of this set is not possible as an independent set. In linear algebra class, we've studied when you're having a collection of independent elements, we can go for extending that set to further up to the dimension of the space. That means if you are having a three-dimensional space and you got two independent elements, by adjoining one more element which is not in the span of the first two elements will give us a linearly independent set which containing three elements. So like that we can go on. So if such an extension is not possible means we will say that the set is a maximal set of linearly independent vectors in E. Okay, now we have considered such a case here. So that is, there is no linear independent extension of this set. Then the number n is invariant and it is called the dimension of the space E. So we have studied by theory in linear algebra, if a space is of n dimension, the maximum number of independent element you can take is n. So that n is going to be the dimension of the space E. And we will write it as dimension of E, that is dim of E is equal to n. And we say that the vectors xi from 1 to n form a basis of E. Now, any element x belongs to E can be represented uniquely as a linear combination of basis vectors. You have studied basis, dimension, everything. So I'm not repeating the same thing. That is, we can write that x as a linear combination of elements from your basis. Remark: a linear space is said to be infinite dimension if it contains an infinite number of linearly independent vectors. I repeat, a linear space is said to be of infinite dimension if it contains an infinite number of linear independent vectors. So this is our part 1 of the introduction. Just we have discussed some of the linear algebra ideas over here. So next class 2 we have to go for furthermore introductory parts or the preliminary parts of linear algebra. Okay, today I am closing here. Thank you for your patient listening, and you're having any Anything missing in between these lines means just free to ask me. Okay, thank you. Quotient spaces. For a subspace E1 of E, we define the quotient space of E with respect to E1 as E by E1, where E by E1 is defined as set of all equivalence classes X, you can say set of all X such that X belongs to E. Here one X means it is of the form X plus E1 called the cosets of A. Cosets of E. So as this bracket X means it is going to be the coset of E. So E by E1 means the collection of those cosets of elements of E. Now two cosets X and Y are either disjoint or coincides. So if there exists an element in the intersection means then Z belongs to your coset X and Z belongs to coset Y. Now if Z belongs to coset X means Z is equal to some X plus P where this P belongs to E1 and therefore X minus X is equal to P which belongs to E1. We will get Z minus X that's equal to P that belongs to E1. Similarly, Z minus Y also belongs to E1. Therefore, Z minus X minus Z minus Y also belongs to E1, which implies Y minus X belongs to E1. Now consider A belongs to your coset X. Then if A minus X belongs to E1, which implies A minus X belongs to E1. Now A minus Y can be written as A minus X minus Y minus X. This is again belongs to E1, which implies A belongs to Y plus E1, which implies A belongs to the cosets of Y. Therefore, coset of X is contained in coset Y. Similarly, we can prove the other way inclusion. So, either two cosets should be identical or disjoint. Now we are defining a linear structure on E by E1 by the coset addition, that is x coset of x plus coset of y is equal to coset of x plus y, and a into coset of x is equal to coset of ax. Now as a remark, the coset of 0 is the 0 vector of the new space E by E1. Coset 0 is the 0 vector of the new space E by E1. The dimension of E by E1, or we'll say the quotient group. We have defined that in that way. Is the quotient space. Yeah, quotient space we have defined. So we will call this as a quotient space. So the dimension of this quotient space E by E1 is called the codimension of E1. It's called the codimension of E1 with respect to E, and we denote it as codimension of E1 with respect to E, or we will say that dimension of E by E1 or codimension of E1 if E is very evident. Some examples. Consider C and C0. C means set of all convergent sequences and C0 means set of all sequences which converges to 0. Now suppose we are taking C by C0. So C by C0. Now X belongs to C, then X is of the form some Xn 1 to infinity form. Now X plus C0 that's equal to A into 1 plus C0. I repeat, now x plus c0. X plus c0 means it's a coset. So it belongs to a coset. Coset determined by x. Okay. Now x plus c0 is equal to a into 1 plus c0. where a means limit of the sequence xn and 1 is the constant sequence with all its terms equal to 1, and 1 is a constant sequence with all its terms equal to 1. Thus, the coset of x can be written as set of all x plus c naught such that x belongs to c, and that can be written as a into coset of 1. That means codimension of c naught by c or codimension of c naught is 1. Now next definition, the vectors x1, x2, etc., xn are said to be linearly independent related to the subspace E1 subspace of E if from sigma I equal to 1 to n ai xi belongs to E1, it follows that a1, a2, etc., an equal to 0. So up to now we have studied the linear independence of vectors in a vector space. Now we are studying the linear independence of these vectors relative to a subspace. That means if you are having sigma I is equal to 1 to n ai xi is in E1, then a1, a2, etc. an equal to 0 means we will say that these vectors x1, x2, etc. xn are linearly independent related to a subspace E1. Now lemma 1.1.4, the dimension of E by E1 is n if and only if there exist x1, x2, etc. xn linearly independent vectors. So the dimension of E by E1 is n if and only if there exist x1, x2, etc. xn linearly independent vectors relative to E1 such that for every x belongs to E, there exists a unique set of numbers a1, a2, etc. an and a unique vector y in E1 such that x can be written as sigma I is equal to 1 to n ai xi. That is nothing but the linear combination of vectors xi plus some y. Moreover, the cosets x1, x2, etc. xn be a basis of E by E1. Now its proof. What we want to prove is that first of all x can be written in this fashion and this will form a basis of your E by E1. So proof. First we consider this as a basis of E by E1. Then the vectors xi for I is equal to 1 to n are linearly independent relative to E1. Because if you are writing sigma I equal to 1 to n ai xi belongs to E1, then sigma ai into, since this is going to be the basis, we are writing an element as a linear combination of the cosets. So this can be written as sigma I equal to 1 to n ai xi coset, and that is nothing but 0, and hence why we are having this to be 0, because in a quotient space we know that even E by E1, when you are considering E1 is going to be the 0 over there, and hence a1, a2, etc. all are equal to 0. Since this is 0, we are having this belongs to E1. So in E1, if means you will get a1, a2, etc. all are going to be zeros. Now for every coset x, we have left the coset of x is equal to sigma I equal to 1 to n ai into xi. That means this is the basis element. So this can be written in this way, and now we have the coset of x is equal to coset of sigma I equal to 1 to n ai xi, and in set notation it can be written as sigma I equal to 1 to n ai xi plus yi for yi belongs to E1. Therefore, x can be written as sigma I equal to 1 to n ai xi plus some y for some y belongs to E1. Now we want to show that such a representation is unique. We have expressed x in our desired form. Now we will prove that such an expression is unique. If suppose X can be written as sigma I equal to 1 to n bi xi plus some set for some set belongs to E1. Then we can subtract these two, so you get 0 is equal to sigma I equal to 1 to n ai minus bi into xi plus y minus z. That is sigma I equal to 1 to n ai minus bi into xi is equal to z minus y. Z belongs to E1, y belongs to E1. E1 is a subspace, therefore we will say that this belongs to E1. So sigma I equal to 1 to n ai minus bi into xi belongs to E1. That implies ai minus bi is equal to 0 and z minus y is equal to 0, which implies a is equal to bi and z equal to y. Such a representation is unique. Now conversely assume that for each x belongs to x, x can be written as some sigma I equal to 1 to n ai xi plus some yi. Now this hold for x1, x2, etc. xn linearly independent relative to E1. The cosets x1, x2, etc. xn are linearly independent since if we are taking the summation I equal to 1 to n ai, the coset of xi means it can be written as the coset of sigma I equal to 1 to n ai xi, and this equal to 0 coset. Then sigma I equal to 1 to n ai xi belongs to E1. Now this belongs to E1, hence A1, A2, etc. An equal to 0. And let x be an arbitrary coset, then x minus sigma I equal to 1 to n ai xi belongs to E1. Therefore, the coset of x is equal to sigma I equal to 1 to n ai xi, and that can be written as sigma I equal to 1 to n ai into coset xi. Therefore, the cosets x1, x2, etc. xn form a basis of E by E1. So we have proved that the dimension of E by E1 is n if there exists a x1, x2, x3, xn linearly independent vectors related to E1 such that for every x belongs to E, there exists a unique set of numbers a1, a2, etc., an and a unique vector y in E1 such that x is equal to sigma I equal to 1 to n ai xi plus y. Moreover, we have proved that the cosets x1, x2, etc. xn is a basis of E by E1. Okay, now we will move to normed spaces. We have studied in linear algebra what's the norm in terms of your inner products. I'm sorry, not in inner products. We have studied normed spaces. So a norm x for x belongs to E is a function from E to R satisfying the following properties. This property we have already studied. That is, first one is positivity. That means norm of x should be always greater than or equal to 0, and if norm of x is equal to 0, even only if x is equal to 0. And second one, norm of lambda x is equal to mod lambda into norm x, and norm of x plus y is less than or equal to norm of x plus norm of y. This is called the triangle inequality. For this is valid for all x comma y in E. and for all lambda in your scalar field. Now with this norm, we define distance between 2 points x and y. That is dxy we will define as norm of x minus y. Now by the triangle inequality we will get norm of x minus y can be written as norm of x minus z plus z minus y. Now we can split the norm by using triangle inequality. We will get this is nothing but d of xy. So d of xy is less than or equal to d of xz plus d of zy. Therefore, d of xy is less than or equal to d of xz plus d of zy. Now we will use the notation as x for the normed space. That means SA together with a norm. We will say this is a normed space. Now hereafter when we are say writing X means its meaning is that it is a normed space. So X is equal to E comma the norm. Now definition 1.2.2, that means the comparability of norm. The norm, one norm, is said to be stronger than two norm if there exists constant c greater than 0 such that norm 2 is with respect to a norm of x with respect to the second norm is less than or equal to c into norm of x with respect to the first norm for all x belongs to E. That is two norm. We are taking norm 1 and norm 2 and we say that the first norm is stronger than the second norm, means the second norm with a norm of an element with respect to the second norm should be less than or equal to some constant times some norm of first x where the constant should be greater than 0. Now the norm, this norm, one norm and two norm are said to be equivalent if there exists a constant small c and capital C both greater than 0 such that c into norm of x with respect to the two norm should be less than or equal to norm of x with respect to the first norm, which is less than or equal to capital C into norm of x with respect to the two norm for all x belongs to E. So with this I'm stopping today's class, and next class we can discuss some more detail about functional analysis. Okay, thank you. Yes. On a space C0, C and L infinity, we define the norm to be the supremum of the absolute value of the terms of the sequences. That means we are defining, if the sequence AI is given, we are defining norm as supremum of mod AI. To check whether this is a norm or not, what we want to do is consider norm. By definition, norm is equal to supremum of mod A1, mod A2, etc. Therefore, each AI is greater than or equal to 0. Therefore, supremum of this quantity is also greater than or equal to 0. Therefore, norm of that quantity is greater than or equal to 0. Now, equal to 0 also you can take because equal to 0 means supremum equal to 0 means this quantity is equal to 0. That means your norm of x should be equal to 0. Now lambda x, take norm of lambda x, that is nothing but lambda into ai from 1 to infinity, that's equal to mod lambda into norm of ai from 1 to infinity. Now this is nothing but norm of x, so it will reduces as lambda into norm of x. For the triangle inequality, consider x comma y belongs to L infinity. Then x equal to some sequence and y equal to another sequence. So x equal to ai from 1 to infinity and y equal to bi from 1 to infinity. Now by definition, norm of x plus y is equal to norm of ai plus bi from 1 to infinity, and that's equal to supremum of mod ai plus bi. from 1 to infinity by definition. And this quantity is less than or equal to supremum of mod ai plus mod bi. That's equal to supremum of mod ai plus supremum of mod bi. Now by definition this is nothing but mod x plus mod y. Therefore we are getting the triangle inequality as norm of x plus y less than or equal to norm x plus norm y. Hence norm is equal to supremum of mod ai is a norm. Now for the second example, consider the space C of closed interval closed interval 0, 1. We define the norm of the function f to be f is equal to maximum of mod f of x where t belongs to closed interval 0, 1. We are defining as maximum. Now this will become a norm. Now consider L1, the space L1. That means it is of infinite tuple space from real numbers with the norm 1 norm. And the 1 norm is defined as 1 norm is equal to sigma I equal to 1 to infinity mod of xi. Exactly it is xi raised to 1 should be the, since it is 1 norm, we should write 1, 2 norm means we should write here 2, like that it will follow. Now this quantity is finite. Less than infinity meaning is this quantity is finite. Then this is a norm on L1. We can check whether it's a norm or not. First condition is we want to check that this norm is greater than or equal to 0, evidently because you are taking summation of those terms whose modulus value. So evidently this is greater than or equal to 0. Therefore the summation is also greater than or equal to 0. Therefore one norm of x is always greater than or equal to 0. Now consider lambda x. Lambda x means the sequence lambda into xi from I to infinity, 1 to infinity. Then norm of lambda x with 1 norm is equal to sigma I equal to 1 to infinity norm of mod of lambda xi. That's equal to lambda can be taken out from this summation. That's equal to lambda into sigma I equal to 1 to infinity mod xi. So this quantity is nothing but the norm of x with one norm. So that is lambda into 1 norm. So second property is also satisfied. Now for triangle inequality, x comma y belongs to L1. Now x can be written as xi from 1 to infinity and y can be written as yi from 1 to infinity. Then norm of x plus y with one norm is equal to sigma I equal to 1 to infinity mod xi plus yi, which is less than or equal to triangle inequality for the modulus we can apply. Then from this we can go for the definition of norm. Then we will get this is a norm. Now here is an important note. Note says that for the one norm we have proved, but if it is p norm means I have said sigma mod xi raised to p should come. Then for that here we have used the idea of triangle inequality for modulus value. See here, but in that cases, in if your second norm, third norm and all is coming means here we should have a quantity this thing raised to. In that case we cannot split it like this. So there is a complication in that case. So we have written here now it is not so trivial that for p greater than 1 norm p is a norm. Now to prove this is a norm we need few more inequalities. So first inequality is Holder's inequality. This Holder's inequality is having two versions. One is in summation and another one is in integration version. So theorem 1.2.3 is a summation version and theorem 1.2.4 is in integration version. Okay. For every sequence of scalars ai and bi and for 1 less than p less than infinity, we have mod of sigma AKBK is less than or equal to sigma mod of AKBK, which is less than or equal to sigma mod AK raised to P whole thing raised to 1 by P and sigma mod BK raised to P whole thing raised to 1 by P, where 1 by P plus 1 by Q is equal to 1. So its proof is, we want to prove this inequality. This inequality only we want to prove with the condition 1 by P plus 1 by Q is equal to 1. So we will have given 1 by P plus 1 by Q is equal to 1. Therefore, taking LCM and all, we will get Q plus P is equal to PQ, or further P is equal to PQ minus Q, or Q into P minus 1. So P is equal to Q into P minus 1. That the one result we need. And further 1 by Q into P minus 1 is equal to 1 by P. That's equal to 1 by P is plus 1 by Q is equal to 1. So 1 by P can be written as 1 minus 1 by Q. So 1 by P minus 1 is equal to Q into 1 minus 1 by Q. That is, by multiplication you will get Q minus 1. So 1 by P minus 1 is equal to Q minus 1. Take that to be as result B. Now what we want to prove is, see, this inequality. Now we will take this inequality as Ci, this term as Ci, and this term as Di. Okay. So here we are taking Ci equal to mod Ai by sigma Aj raised to P whole thing raised to 1 by P, and Di as mod Bi by sigma Bj raised to Q whole thing raised to 1 by Q. These two terms occurred in the inequalities right hand side. So we are taking first one, Ci is mod Ai by one term and Di is mod Bi by this term. Now if you are calculating sigma of Ci raised to P, Ci raised to P means I should have Ai raised to P, and this 1 by P will get cancelled. Now applying summation, this is a constant. I will get the numerator as sigma mod Ai raised to P by, here 1 by P has been gone, so sigma Aj raised to P, both are same. So I will get this to be as 1. And the same manner for sigma Di, I will get this to be as 1. Mark that as equation C. Now to show the first inequality, it is enough to show that sigma Ci Di is less than or equal to 1, because sigma Ci Di means is mod Ai mod Bi will come, so mod of Ai Bi will come, which is less by sigma Aj raised to P raised to 1 by P into sigma mod Bj raised to Q raised to 1 by Q will come, which is less than or equal to 1 means you can take the denominator to this side, you will get the desired inequality. So here what we need to prove is that sigma Ci Di is less than or equal to 1. So we will prove this quantity. Now firstly we will show that Ci Di, that product is less than or equal to Ci raised to P by P plus Di raised to Q by Q. For that, consider the function y equal to x raised to P minus 1. Y equal to x power P minus 1. Suppose we are integrating that with respect to x from 0 to Ci, we get the area under the curve. So the area is S1 equal to integral 0 to Ci x raised to P minus 1 dxi. Its integration will result 1 by P into Ca raised to P. Similarly, integrating the inverse one, that is x equal to y raised to 1 by P minus 1, that is equal to y raised to Q minus 1 with respect to y, from 0 to Di, we have the area S2. So if you're marking these two area, it may come like this. S1 means this green shaded portion and S2 means this entire portion including the red one. Now what about our Ci into Di? Ci into Di means you will get this rectangle. Now taking this two area summation S1 plus S2, it is having some excess amount. That is this red portion, red shaded region is extra. So by geometric interpretation we will get S1 plus S2 is always exceed the product CIDI. That is CIDI is less than or equal to Ca raised to P by P plus Di raised to Q by Q. So we have proved this inequality. Now when will this equality will hold? The equality will hold if Di is equal to Ca raised to P minus 1. So after substitution dA equal to Ca raised to P minus 1. You can see that it will become Ca into Ca raised to P minus 1. This side also Ca raised to P minus 1 into Q. P minus 1 into Q we have studied that to be as PQ minus Q, that is again will result P. So Ca raised to P into 1 by P plus 1 by Q will come. But 1 by P plus 1 by Q is 1. So Ca raised to P will come. Now adding up two with respect to I, we get sigma over I, CIDI is less than or equal to 1 by P into sigma over I, Ca raised to P plus 1 by Q, sigma over I, Di raised to Q. Now this is nothing but when you're having this summation, we have seen that from inequality C, this thing is going to be 1 and this is again going to be 1. So we will get 1 by P plus 1 by Q, that's equal to 1. So we have proved that sigma CIDI is less than or equal to 1. This is the only thing that we want to prove. Hence the oldest inequality. See from here, if you are substituting your CIDI values and you will get something in the denominator. Now take the denominator times to be this side, you will get the Holder's inequality. Now remark, suppose your P value and Q value are equal to 2. Then this inequality will become the Cauchy-Schwarz inequality that we know or we have come across many times. So sigma AKBK is less than or equal to sigma mod AK into sigma mod BK. Now remark 2. Here we have defined this Holder's inequality up to 1 less than or equal to P less than infinity. But for infinity curves too we can define this quantity. So in terms of you're taking this to be as supremum of BK. So this term has to be replaced with supremum of BK. Then also the Holder's inequality will be valid, that we will see afterwards. Now I have said that Holder's inequality has got two forms. One is in summation form, another form is in integration. So here is the integration part. Theorem 1.2.4. Let 1 less than P less than infinity and let Q be such that 1 by P plus 1 by Q is equal to 1. Then for all functions f comma g on an interval closed interval a b such that the integral a to b mod f of t raised to p dt and integral a to b mod g of t raised to q dt and integral a to b mod of f of t g of t dt exist as Riemann integrals. We have integral a to b f of t gt modulus of that is less than or equal to integral a to b mod of f of t power p dt all thing raised to 1 by p and integral a to b mod g of t power q dt all thing raised to 1 by q. So this is the inequality that we want to prove. And here one more thing we want to notice that in Riemann integral integral a to b f of t g of t dt also exists, then this inequality, this modulus of this is less than or equal to integral of mod of this. So combining that, we will get modulus of integral a to b f of t g of t dt is less than or equal to integral a to b mod of f of t power p dt all thing raised to 1 by p into integral a to b modulus of g of t power q dt all thing raised to 1 by q. So Riemann integration, uh, we are having a partition of the interval. We will partition that into n equal subintervals and such that a is equal to starting is x naught and the last one is xn is b. And we will have the delta x quantity as b minus a by n. That and all we have fixed. Now we have sigma I equal to 1 to n mod of f of xi g of xi into delta xi. This quantity is less than or equal to sigma I equal to 1 to n mod of f of xi g of xi into delta x raised to 1 is there. I can replace that 1 with 1 by p plus 1 by q. So I have replaced delta x raised to 1 as 1 by p plus 1 by q. And in next stage, what I'm going to do is I will separate the delta x. I will write delta x raised to 1 by p plus 1 by q as delta x raised to 1 by p into delta x raised to 1 by q. So this will become sigma I equal to 1 to n mod of f of xi raised to p into delta x whole thing raised to 1 by p into here one modulus term is missing. Okay, here one modulus is there. So it will be modulus of g of xi raised to q into delta x all thing raised to 1 by q. Now we have the Holder's inequality for this thing. Applying that, we will get Holder's inequality means just before what we proved. We will get sigma I equal to 1 to n modulus of f of xi raised to p into delta x raised all thing raised to 1 by p into this quantity as such is less than or equal to sigma of this one into sigma of this one. Okay, call it as double star. First one you star, this one double star. Now from star and double star, what we get is sigma I equal to 1 to n modulus of f of xi g of xi into delta x is less than or equal to this quantity into this quantity. Now we know that as to get the integration, Riemann integration, what we have to do is we will go for the partition to be finer and finer. That means our n value should tends to infinity. So as n tends to infinity, we get integral a to b f of t into g of t dt is less than or equal to integral of mod f of t power p dt all thing raised to 1 by p into integral of modulus of g of t power q into dt all thing raised to 1 by q. Thus we have proved the Holder's inequality for functions having, which is Riemann integrable functions f, g and fg. Okay, so I'm closing today's session. Thank you for your patient listening. If you're having any doubt or queries means, please do time to ask. Thank you. Is Minkowski's inequality. It says that for every sequence of scalars a equal to ai and b equal to bi, and for 1 less than or equal to b less than or equal to infinity, we have a plus b norm of that with respect to the p norm. P norm means you are having your p norm of x. You are taking your x with one norm we have already proved. So with respect to P norm means having the norm definition as P norm is equal to, you want to go for sigma summation sum j equal to sum 1 to n 1 to n mod of xj mod of xj raised to p. Should I want a bracket? So xj raised to p whole thing raised to 1 by p. Okay, so this was our definition for norm of this 1 by p. So what for we are proving this and all means this inequality means actually in the last class we have studied Holder's inequality. With that Holder's inequality only we will prove the Minkowski's inequality. Now you know when a norm is defined with respect to this norm we can define a metric. So in order to prove the triangle inequality of the norm space or the metric space, we need these two inequalities, that is Minkowski's inequality. Next class we will prove that with respect to this norm, we will define the metric. Metric you can define as d of xy is equal to norm of x minus y with respect to p norm. Then we will prove that that's a metric space or that is a metric. So here what we want to prove is norm of a plus b with respect to the p norm is less than or equal to norm of a with respect to p plus norm of b with respect to p. In this class we will concentrate only on Minkowski's inequality. So here we want to prove, first of all you want to understand the difference between Minkowski's and Holder's inequality. In Minkowski's inequality, we are having here plus notation. So this is we are having the plus notation. But in Holder's inequality, we are having the multiplication notation there. Thus, when you expand this, we want to prove that sigma j equal to 1 to n mod of aj plus bj raised to p whole thing raised to 1 by p is less than or equal to sigma j equal to 1 to n mod aj raised to p whole thing raised to 1 by p into sigma j equal to 1 to n mod bj raised to p whole thing raised to 1 by p. Now we will focus on the case. See here it's given the variation for p is from 1 to infinity. So first we will check what will happen if p is equal to 1. Now if p is equal to 1 we should substitute here 1, here also 1. So it will reduce us as nothing but you know that mod of aj plus bj is less than or equal to mod aj plus mod bj. That is the triangle inequality. So we can apply it here. So we'll get sigma j equal to 1 to n mod aj plus bj is less than or equal to sigma j equal to 1 to n mod aj plus sigma j equal to 1 to n mod bj. Reason is mod aj plus bj. First we have splitted this, then we are taking the summation. Now take the case if 1 equal p equal to 1 we have proved. So take the case p equal to infinity. Now p equal to infinity means our norm definition will change as instead of taking this sum we will take the suprema. Since here we have got only the finite number of terms, we can take the maximum function. So that norm definition will become maximum of aj plus bj mod of aj plus bj j equal to 1, 2, 3 extra up to n is less than or equal to maximum of mod aj plus maximum of mod b. This also the subadditivity of maximum function. You want to find the maximum of aj plus bj. That value should be always less than or equal to maximum of aj plus maximum of bj. Thus we have proved the inequality for the case p is equal to 1 and p equal to infinity. Next we want to find whether this inequality is holding in the case of 1 less than p less than infinity. So here is the one. So we are taking 1 less than p less than infinity. Now norm of a plus b raised to p is equal to, so we are taking raised to p, so no need of writing raised to 1 by p over here. So we are having sigma mod ak plus bk raised to p. Now this can be splitted into mod ak plus bk raised to p minus 1 into mod ak plus bk. Can you follow? This can be written as raised to p minus, if I am writing, I will get one more mod ak plus bk. Now I can split that mod ak plus bk as mod ak plus mod bk. So this entire quantity will become less than or equal to sigma mod ak plus bk raised to p minus 1 into mod ak plus mod bk. Now if we are having such a quantity, we can multiply that. So we are having the multiplication, that's equal to sigma mod ak plus bk raised to p minus 1 into mod ak plus sigma mod ak plus bk raised to p minus 1 into mod bk. Now we can apply Holder's inequality for this term. See, this is a term which can be applied for your Holder's inequality, and this term also we can apply our Holder's inequality. So when you are applying Holder's inequality for this term, you will get, before that we can reverse it. That is, first I will write mod ak, then I will write this. That will explain you after this why I am writing like this. Okay. So first of all, I am writing mod, same expression. Instead of this one, I am writing mod ak into mod ak plus bk raised to p minus 1 plus here also sigma mod bk into. Now I will apply Holder's inequality. Now applying Holder's inequality means I will get this quantity is less than or equal to, this term is mod sigma mod ak raised to p whole thing raised to 1 by p, and this quantity sigma of this quantity raised to q whole thing raised to 1 by q, and this quantity also I am having sigma mod bk raised to p whole thing raised to 1 by p, and sigma mod ak plus bk raised to p minus 1 whole thing raised to q, and everything raised to 1 by q. So my expression will change like this. Now why I have written that mod ak at first means, see here, when you are multiplying this, that is sigma mod ak plus bk raised to p minus 1 whole thing raised to q. What is that? P minus 1 into q. P minus 1 into q, we have seen in previous class that 1 by q plus 1 by p is equal to 1. So we are having 1 by p plus 1 by q equal to 1. Therefore, what you are having is, when you are taking LCM and all, you get p plus q is by pq is equal to 1. So I am having p plus q I am writing P plus Q is equal to PQ. P plus Q is equal to, I am writing this as PQ. Now if you are finding what is P minus 1 into Q that we want, means we can go for this Q to be this side. So I am getting P is equal to PQ. Okay? Here PQ minus Q. Am I right? PQ minus Q. Now if I am taking my Q as common, I will get P minus 1 into Q. So P minus 1 into Q is getting us P. That is P equal to let us starting P minus 1 into Q. So this inequality we are using here, like P. So this we can replace with P minus 1 into Q will come here. That we can replace with P itself. So my inequality will become this norm A plus B with P norm is less than or equal to sigma mod AK raised to P whole thing raised to 1 by P into sigma mod AK plus BK raised to P. You know that A raised to N or raised to M is A raised to Mn form. So raised to P whole thing raised to 1 by Q and plus sigma mod Bk raised to P whole thing raised to 1 by P into sigma Ak plus Bk raised to P whole thing raised to 1 by Q. Next thing what we are going to do is, in these two expressions this term is common. So we can take that to outside. Okay. See. Thus mod A plus B with P norm is less than or equal to sigma mod AK plus BK raised to P whole thing raised to 1 by Q into common take I have taken outside, remaining is sigma mod AK raised to B whole thing raised to 1 by P plus sigma mod BK raised to P whole thing raised to 1 by P. Now this value is equal to, this is nothing but my norm of A and this is my norm of B by definition. So I can write this as sigma mod AK plus BK raised to P whole thing raised to 1 by Q into norm of A in plus norm of B. What we want to prove? I want to get norm of A plus B is less than or equal to norm A plus norm B. So this part we have got. So I want to reduce this side to be as norm of A plus B to P. So how I will get that one? See, to here only we have C. Now suppose we are dividing both sides with this sigma mod AK plus BK raised to P all to raised to 1 by Q. What will happen? This is exactly the same, right? So we are having this quantity is nothing but sigma mod AK plus BK raised to P whole thing raised to 1 by P. So this quantity will reduces as sigma mod AK plus BK raised to P whole thing raised to, here we are having 1. So 1 minus 1 by cube form. I'm writing, see, we are dividing this with this, we are having sigma mod AK plus BK raised to P by sigma mod AK plus BK raised to P whole thing raised to 1 by q is less than or equal to mod A plus mod B. So norm A plus norm B. Now this is equal to see sigma mod AK plus BK raised to P whole thing raised to 1 minus 1 by Q, which value is less than or equal to norm of A plus norm of B. Now this quantity 1 minus 1 by Q is 1 by P. Since 1 by P plus 1 by Q is equal to 1, so 1 minus 1 by Q is 1 by P. So we are having which is less than or equal to norm of A with respect to P plus norm of B with respect to P. Thus, this is nothing but norm of AK plus BK. Thus, we got norm of AK plus BK is less than or equal to norm of A plus norm of B. As I have said, this inequality we are using for proving our norm P is a norm, and we will use this inequality especially for proving the triangle inequality. Now we will pass to the next Minkowski's inequality in terms of integrals. So integral, that is given in theorem 1.2.6. For all 1 less than p less than infinity and all functions f, g on an interval closed interval ab for which the integral a to b mod f of x raised to p dx and integral a to b mod g of x raised to p dx exist, the integral mod a to b mod f of x plus g of x raised to p dx exists if these three integrals exist, and this will satisfy integral a to b mod f of x plus g of x raised to p dx all things raised to 1 by p is less than or equal to integral over a to b mod f of x raised to p dx all things raised to 1 by p plus integral a to b mod g of x raised to p dx all things raised to 1 by p. So this is the quantity that we want to prove. So we are using the Riemann integral concepts. So first of all, we will partition the closed interval AB into n number of partitions with each of equal length. So I'm dividing my AB as A equal to x0 which is less than x1, which is less than x2, etc. which is less than xn, and that xn is equal to B with the interval length delta x equal to b minus a by n. That means all are equal intervals. Now we are having the inequality norm of a plus b with respect to p norm is less than or equal to norm of b plus norm of b. This we got from the Minkowski's inequality previous question. Now if this is the case means we can say like this. Instead of a plus a and b, you can take f of xi and g of xi. So sigma I equal to 1 to n mod f of xi plus g of xi raised to p into delta x whole thing raised to 1 by p is less than or equal to sigma mod f of xi raised to p into delta x whole thing raised to 1 by p plus sigma mod g of xi raised to p into delta x whole thing raised to 1 by p. Now as usual what we will do is we will go for the partition to be finer and finer. That means we will say that when n tends to infinity, the partition length become very small. So we are going for that. Now as n tends to infinity, what we will get is integral a to b, your summation will become integral and this part will become your dx. So integral a to b mod f of x plus g of x raised to p into dx whole thing raised to 1 by p is less than or equal to, at limit n tends to infinity, summation will become integral. So integral a to b mod f of x raised to p dx all thing raised to 1 by p plus integral a to b mod g of x raised to p dx all thing raised to 1 by p. As I have said, so this is the inequality that we want to prove. So we have proved that. So as I have said, in order to avoid the confusion between Holder's inequality and Minkowski's inequality, you should take care of two things. One is that in Holder's inequality, here we are having the multiplication symbol, but in Minkowski's inequality, we are having addition. And further, in Holder's inequality, we are having two things here, that is 1 by p raised to p raised to 1 by p and raised to q raised to 1 by q term. But in Minkowski's inequality we are having only p term, that is norm of mod of f of x raised to p all thing raised to 1 by p. Here also mod of g of x raised to p all thing raised to 1 by p is coming. So don't get confused with Holder's inequality and Minkowski's inequality. Now we will see some of the topological and geometric notations. This you have studied under your real analysis course under the topic of metric space. So a sequence Xn of a normed space X converges to a point X in X if and only if Xn minus X converges to 0, norm of that converges to 0 as n tends to infinity. So what is this meaning? You might have studied that for the convergence of sequence there exists a natural number n belongs to n such that d of xn x is less than epsilon for every n greater than or equal to that capital N. So here also saying the same, because when you are taking norm of xn minus x means it is nothing but the distance between xn and x, that is d of xn x. So this is nothing but d of matrix of xn and x. So what this expression say is comma x, I should write. Okay. Now what this expression says is this distance tends to 0. That means distance is going very small and small. That is, you can say that d of x and x is less than epsilon. And as n tends to infinity means after some stage it will occur. And second one, an open ball of radius r greater than 0 centered at x0 is defined to be the set. Let's study this too. But here we are using the notation as dr of x0. Notation as dr of x0. So dr of x0 is equal to set of all x belongs to x such that norm of x minus x0 is less than r. Again, norm of this means this is nothing but d of x comma x0 is less than r. So it is an open ball of radius r greater than 0. And third concept, a set O subset of x is said to be open if and only if for every x belongs to O there exists r greater than 0 such that drx is contained in O. That is, it says that if O is said to be an open set, if O, every member of O, we can find an open ball of radius r which completely contain inside your set O. It's nothing but gives the definition of open set. And here its complement. F subset of X is said to be closed whenever for a sequence we will say that its complement is open. That is also true, but we are having the exact definition of a closed set means for every sequence xn belongs to F that converges to some x belongs to X follows that x belongs to capital F. In metric space classes, we have studied that a set F is said to be closed if F contains all its limit points. So limit points means if X is said to be a limit point, then there exists a sequence Xn in X such that that sequence Xn converges to X. So that's the definition for the limit point. And in terms of sequence, now this definition says that F contains all its limit points. That means F is closed. I repeat, a set F is said to be closed if every sequence in F that converges to some x belongs to X, then that X should contain in F. So we want to go through some more definitions that we will discuss in our next class. And today I am winding up. So thank you for your patient listening. Here's the lemma 1.3.1. If O is an open set, then the set F equal to complement of O is closed. Conversely, if F is a closed set, then the set O is equal to complement of F is open. This we are repeatedly using in your topological class, but we haven't proved it. Very easy to prove. The proof is like this. First we assume that O is an open set. Assume that O is an open set. Now if F equal to complement of A and let Xn belongs to F and Xn is converges to X in X, then we claim that then this X belongs to F. If not, what will happen? If X is not belongs to F means then X should belongs to your O. Then for some R greater than 0, we have assumed that O is an open set. Okay. So for some R greater than 0, we can find an open ball drx which would be completely contained inside your O. Okay, so the distance between xn and x should be less than r. Distance between xn and x should be less than r. Since we are having an open ball completely contained inside your O, so the distance between xn, that sequence xn and x should be less than r, which implies xn belongs to O. Am I right? Xn belongs to O. But we have taken the sequence in F. See, Xn belongs to F only you have taken. But F is going to be the complement of O. Now we are getting this Xn belongs to O, which is a contradiction. Which implies Xn belongs to O. Which implies Xn does not belongs to F, which is a contradiction. Therefore, this X should belongs to F. Then by our definition of a closed set that we have discussed in your previous class, this F is closed. Conversely, assume that F is a closed set and let O is equal to complement of F. Now we want to prove O is open. Now we will show that for every x belongs to O, there exists epsilon greater than 0 such that d epsilon of x, that's an open ball which is completely contained inside your O. Suppose not, what will happen? Let us discuss. Then for every, you can take the sequence epsilon and which is decreasing to 0. See, you can take 1 by n also, no problem. There exists xn belongs to f such that distance between xn and x is less than epsilon. Since we have taken, what we assumed is f is closed. Assume that f is a closed set. Since f is a closed set means every sequence in that will converges to f itself. So you have taken here a sequence epsilon n and a sequence xn. So distance between xn and x is less than epsilon n. Now its meaning is that epsilon n is a decrease, and that means 1 by n as n tends to infinity form. So that means the distance between xn and x is very less, or xn converges to x. Now, therefore, since f is closed, this x should belongs to f, which is again a contradiction since we have assumed that x belongs to O and O is the complement of f. This what we got is there exists d epsilon of x which is completely contained inside O, which implies O is open. So we have proved if O is an open set, then its complement F is closed, and if F is a closed set, then its complement O is open. Now from the topology we know that collection of arbitrary union of open set is open and finite intersection of open set is open. Okay, that we are noting here. Note that the union of open set is open and the intersection of closed set is closed. That means we are taking only finite numbers. And the empty set and the whole set are both open and closed. Okay, empty set and whole set X are both open and closed. Now we are defining closure. Closure we have seen in topological class and reanalysis class as the set of all closed intersection of set of all closed sets which contain A. Here we are giving another definition, but both are same. The closure, a closure of a set A is the set of all x belongs to x such that there exists a sequence xn in A with xn converges to x. That means we are collecting only the limit points of x. Is the set of all x belongs to x such that there exists a sequence xn in A with xn converges to x. Now we call a set A subset of x is dense if and only if A closure is equal to x. It's a familiar definitions for you. A closure, and when we say that a set is dense. Example for a dense set also, you know, set of rationals is dense in a set of real numbers. Next is prove that norm is a continuous function. So in order to check the continuity, we will prove that if a sequence xn converges to x, then f of xn converges to f of x, then we will say that the sequence, the function is continuous. So here also we are having the same strategy for proving norm to be a continuous function. So we will assume that in the normed space X with the norm, in the sequence xn converges to x. Now we want to prove norm of xn converges to norm of x. So assume that xn converges to x in the normed space x comma with the norm, which implies by definition norm of xn minus x is converges to 0 as n tends to infinity. Now take norm of xn minus norm of x, its modulus. Once you find norm means it will be a scalar quantity. Then we can go for the mode of that. Now norm of xn minus norm of x is less than or equal to norm of xn minus x. Now our proof is over. That means this quantity converges to 0. That means this quantity converges to 0 as n tends to infinity. Implies that this quantity also converges to 0 as n tends to infinity. That means your norm of xn converges to norm of x. So here is second problem. Prove that dp of x comma y is equal to sigma j equal to 1 to n mod xj minus yj raised to p whole thing raised to 1 by p is a metric on Fn. In order to prove a metric space, what do we want to prove? First, we want to prove if dp of, and denoting the metric as dp. So dp of x comma y is greater than or equal to 0, and if dp of xy is equal to 0, then x equal to y. Let us see the first condition. So dp of xy is always greater than or equal to 0. But the reason is, when you're finding mod of xj minus yj, it will result always positive or non-negative quantity. That means, now if you're taking the power of a non-negative quantity, that will again result a non-negative quantity. Now summation of that non-negative quantity, again non-negative. Now raised to 1 by p, again you will get a non-negative quantity. So dp of xy is always greater than or equal to 0. Now if we are applying that dp of xy equal to 0, what will happen? That means sigma j equal to 1 to n xj minus yj raised to p is equal to 0, which implies mod of xj minus yj is equal to 0. That means xj is equal to yj for every j. So xj is equal to yj for every j implies x equal to y. So we are getting dp of xy is equal to 0 implies x equal to y. So first condition of your metric space is satisfied. Now we want to get the symmetry. So very evident, since we are having dp of xy is equal to sigma j equal to 1 to n mod xj minus yj raised to p all thing raised to 1 by p. If you are replacing xj with yj and yj with xj, you will get mod of yj minus xj. These two doesn't make any change, but as per definition, this will result dp of yx. Hence, it is symmetric, or dp of xy is equal to dp of yx. Next, we want to prove the triangle inequality. That is dp of xy. Consider dp of xy. Now dp of xy, by definition, it is sigma j equal to 1 to n mod xj minus yj raised to p whole thing raised to 1 by p. Now this is equal to sigma j equal to 1 to n xj minus, we introduce a zj term. So xj minus zj plus zj minus yj raised to p whole thing raised to 1 by p. Now this is the case, we can use which quantity? We can use Minkowski's inequality. So by Minkowski's inequality, this will reduces as which is less than or equal to sigma j equal to 1 to n mod xj minus zj raised to p whole thing raised to 1 by p plus sigma j equal to 1 to n zj minus yj raised to p mod of that whole thing raised to 1 by p. Now by definition, the first quantity is nothing but the metric of x8, that is dp of x8 plus second thing is dp of zy. So dp of xy is less than or equal to dp of xz plus dp of zy. Thus triangle inequality is proved. Therefore dpxy is a metric. Next, here is the definition. We have seen the definition of intervals. Interval property is that if I is an interval, then if a comma b belongs to I, then any number between a and b is also belongs to I. So here is one more definition of an interval. 1.3.2. For 2 points x and y, we introduce the set of all lambda x plus 1 minus lambda into y for 0 less than lambda less than or equal to 1. As you have studied in your convex set classes, which is the line segment joining these 2 points. And we call the set an interval and we write I of xy. So here we have defined the interval. That means if x and y are belongs to I, then lambda x plus 1 minus lambda y also belongs to I. Then we will say that I is an interval. Of course, 0 less than lambda less than or equal to 1. Next is triangle inequality is in an interval will become an equality. There is a mistake. An equality is not an inequality. An equality. So how does this follow? See, this is the case. Suppose your z belongs to the interval I of xy. Then norm of x minus y is equal to norm of x minus z plus z minus y. This is the thing that we want to prove. Since z lie on the line joining x and y. So here is the line joining. This point is x and this the point is y. Since it's a straight line, suppose somewhere here is lying your z. Now since we are taking the straight line distance, this is distance of xy can be split into distance of xz plus distance of zy. Therefore, equality holds. It's very easy to see in geometrical terms. Next definition, convex set. A subset M of a linear space E is called convex if and only if for every 2 points x, y in M, the interval I of xy is contained in M. In your convex set class, you have studied that if a set C is said to be convex if x, y belongs to C, and if lambda belongs to open interval or closed interval 0, 1, then lambda x plus 1 minus lambda y belongs to C. This is also the same thing. Since we have defined the set lambda x plus 1 minus lambda into y as an interval, we can have this definition in this fashion too. That is, a subset M of a linear space E is called convex even only if For every 2 points x, y in M, the interval I of x, y is contained in M. Both the definitions are the same. So note that if MA, that is family of convex set, each MA denote a family of convex set. Then when you take an intersection of such convex set, which is again going to be a convex set. Intersection of convex set is again going to be a convex set. Now for a linear normed space E, D of E, we define this as set of all x such that norm of x less than or equal to 1 is a convex set. So this time we are open ball, right? So how to prove open balls are convex set? So you take 2 points from this open set, x, y. Then this belongs to open set, means norm of these values should be less than or equal to 1. That is, norm of x is less than or equal to 1, norm of y is less than or equal to 1. Now for 0 less than or equal to lambda less than 1, consider norm of lambda x plus 1 minus lambda y. Now this is less than or equal to norm of lambda x plus 1 minus lambda into y. Exactly should come inside your bracket. So I have written wrongly here. Here I should have the bracket. Then my norm will come here. Okay. Here should come my norm. So it's a mistake. Correct it. Now this is equal to, or which is less than or equal to, mod lambda into norm of x plus mod 1 minus lambda into norm of y, and that's equal to lambda into norm x plus 1 minus lambda into norm y. But we know that norm of x and norm of y are less than or equal to 1. So we can replace that. So which is less than or equal to lambda into 1 plus 1 minus lambda into 1. So lambda get cancelled, you get 1. So we got norm of lambda x plus 1 minus lambda into y is less than or equal to 1. That means lambda x plus 1 minus lambda into y belongs to, you said, D of E. See, D of E. That implies D of E is a convex set. Also, D of E is symmetric. That is evident from the definitions. If you know norm of x less than or equal to 1 means either should be x or minus x. So we will say that centrally symmetric. That is, if x belongs to D of E, then minus x is also belongs to D of E. We say that centrally symmetric. Set S of E, that's equal to x such that norm of x equal to 1. Just before you studied less than or equal to, that we will say that open ball. Now this is called unit sphere of E. One more definition. A subset M of a normed space X is called bounded. Already studied this one. When you will say that a normed space is bounded, as a set bounded, you know. Now as a normed space, when we say that this is bounded, if there exists a number c greater than 0 such that for all x belongs to M, we have norm of x is less than or equal to c. So a normed space is said to be bounded If you take any element from the normed space and take its norm, if the norm is less than or equal to some constant, we will say that the normed space is bounded. The last inequality can also be expressed with the inclusion M is contained in C into dx. C into dx means d of x means you know that it's the open part. So M is contained in C into dx. If I get in something like that also, we will say that M is bounded. Okay. So today we have studied some of the concepts from the topology that can be related to your functional analysis. That is, if you're taking a normed space, a bounded normed space, a unit sphere, open ball, convex set, interval, then okay, then metric space, that is dp of xy with p norm is a metric space that we have proved, and the norm of a function norm is a continuous function. Closure definition, open set and closed sets, the relation connecting open set and closed set. We have proved this everything. So today I'm stopping here. So thank you for your patient listening. Quotient normed space. So lemma 1.4.1. If x0 is a subspace of X and x0 is a closed subspace, then the quotient space X over x0 can be equipped with a norm given by the formula norm of X is equal to infimum of Y belongs to x0, norm of X minus Y for X belongs to X over x0. Here we have defined norm. You might have remembering the definition of this bracket X. Okay. That is, if x0 is a subspace of X and x0 is closed, then we can go for the quotient space X over x0. Now X over x0, any element is of the form some bracket X. That is the occurrence class of X. Further, we can say that this X is of the form X plus x0. Now, this norm of such an equivalence class is defined as infimum of y belongs to x0, norm of x minus y for x belongs to x over x0. We want to prove that it's a norm. So, first thing, if norm of your class x is equal to 0, then by definition, there exists a sequence a yn belongs to x, not such that yn converges to x. Now, since norm of x equal to 0, this implies by definition infimum of norm of x minus y is equal to 0 for y belongs to x0. That implies norm of x minus yn equal to 0. That is, yn belongs to x0. You might have remembering in your quotient space, if I am taking x over x0, if this is the fashion means the identity over this quotient space is nothing but x0. Identity is x0. So we will say that x0 is the 0 of x over x0. So here we have got infimum of this equal to 0. That means norm of x minus yn equal to 0. That means this quantity is 0 means for some yn belongs to x naught means this yn should converges to x. But then x belongs to x naught. Since given that x naught is closed, this sequence limit also should contain in x naught since x naught is closed. Therefore, what we get is since x belongs to x naught and x naught is going to be the 0 of this quotient space x over x naught, we can conclude that your equivalence class x is equivalent to 0. Since x belongs to x naught, we can say that your x equivalent class x is of the form x plus y such that y belongs to e naught. That means e naught or x naught, that's equal to z such that z belongs to x naught. Since we have taken already x, so x plus y such that y belongs to x naught means it is of z such that z belongs to x naught. That is nothing but your z naught. Now z, what is z naught? Z over z naught, when you consider z naught is going to be the 0. Now for the norm second condition, we'll say that homogeneity condition for this. That is, we want to prove that norm of lambda x is equal to mod lambda into norm x. Let us see how we can get that. Now, norm of lambda x is equal to lambda into x plus x naught, that's equal to infimum of norm of lambda x plus y such that y belongs to x naught. Now this is equal to infimum of mod lambda. From this you can take mod lambda. Okay, this is already known to be as a norm. Now lambda, mod lambda into norm of x plus, here no lambda is there, so I am putting 1 by lambda into y such that y belongs to x naught. Now x naught is given to be a closed subspace, so it is a subspace. So if y belongs to x naught, 1 by lambda also belongs to x naught. So I can replace this 1 by lambda into y with some other member in my x naught. So I have replaced that infimum of mod lambda into norm of x plus some y dash such that y dash belongs to x naught. So written here the what is the reason? Since x naught is a vector space and y by lambda also belongs to x naught. So what I got is infimum of something, but here we have a constant. So I can write mod lambda times infimum of this quantity, that is mod lambda into infimum of norm of x plus y such that y belongs to x naught. That is nothing but mod lambda into norm of x. That means this will come as the equivalent class of x. So norm of equivalent class of x. Now we want to prove the triangle inequality. That is, we want to prove norm of x plus y is less than or equal to norm of x plus norm of y. So this is the proof technique. For every epsilon greater than 0, we take z1, z2 belongs to x naught. That's for every epsilon we are taking two members from your set x naught. What was x naught? X naught was a closed subspace. So with the condition norm of x plus z1, when you are considering, it should be less than infimum of x minus y such that y belongs to x naught plus epsilon. Since it is valid, since it is going to be as the infimum. Now here again you will get that's equal to norm of x plus z1 is less than or equal to norm of your equivalent class x plus epsilon. and norm of y plus z2 is less than or equal to norm y plus epsilon. Similarly, like following the same definition of infimum, we can have a number z1, z2 and an epsilon in this version. Then for every epsilon greater than 0, we can consider norm of x plus y, equivalence class of x plus y. So by definition it is infimum of z belongs to x naught, norm of x plus y plus z. Now this value is less than or equal to, I can introduce z1 plus z2. So this quantity, such quantity is infimum is this. So this quantity should be always, this infimum should be always less than or equal to this one. So which is less than or equal to x plus y plus z1 plus z2. Now this quantity is less than or equal to, here we can apply your a triangle inequality. Okay, since we have removed this infimum, now this is nowhere is the new norm, it is the old norm that we know. So this norm we can apply the triangle inequality. So this is less than or equal to norm of x plus z1 plus norm of y plus z2. Now this is of the form x plus z1, z1 belongs to your x naught, z2 belongs to x naught. So this is less than or equal to, you can take the infimum of this one where z1 belongs to x naught. So this quantity will reduces as norm of equivalent class of x plus norm of equivalent class of y plus 2 epsilon. This we got from here. Now already proved that this quantity is less than or equal to this. See, this quantity and this quantity we have made use here. So while adding you will get x plus 2 epsilon. Now since epsilon is arbitrary, we can conclude that norm of x plus y is less than or equal to norm of x plus norm of y. So this is the proof. I think you can follow this very easily. Only thing is that we have used here is infimum idea and x naught is closed idea. Okay. This definition, semi-norm. Semi-norm means in your norm definition we are having the condition that norm of x equal to 0 if and only if x equal to 0. If you are violating that condition means we will say that it is a semi-norm. So the formal definition of semi-norm definition, a semi-norm on a linear space E is a function P from E to R plus such that first condition is P of 0 is equal to 0. Second condition, P of lambda x is equal to lambda into mod lambda into P of x. And third condition, P of x plus y is less than or equal to P of x plus P of y. See here, we are having P of 0 is equal to 0. But we don't have the condition P of 0 is equal to 0. P of x equal to 0 if and only if x equal to 0 condition. Okay, so when we avoided that condition, we will get a semi-norm for all x, y belongs to E and for lambda scalar, real number or complex number. See, as a note, we can have here from the definition of norm, if we avoid the condition norm x equal to 0 if and only if x equal to 0, we get a semi-norm. Now as a remark, when we consider E naught, the set of all x belongs to E such that P of x equal to 0, We may many times come across this set in your linear algebra or in abstract algebra classes. Now we will say that this set is the kernel of P. That is set of those elements in E which are mapped to 0. So that is the kernel of P. Then E naught is a subspace of E. These two we have proved. Kernel is a subspace and P of x plus y is independent of y belongs to E naught. If this y belongs to E naught, then P of x plus y is independent of y belongs to E naught. That means if y1 and y2 belongs to E naught, then P of x plus y1 is same as P of x plus y. Here is the proof. For you take y1, y2 belongs to E naught, then P of is a proof for P of x plus y is independent of y belongs to E naught. Okay. For let y1 and y2 belongs to E naught. Then P of x plus y1 that can be written as P of x plus y2 minus y1 plus y1. Now this quantity is less than or equal to P of x plus y2 plus P of minus y2 plus y1. Now this is nothing but P of y2 plus y1 you're considering in E naught. y1, y2 belongs to E naught. So this quantity is 0. So this quantity will reduce as P of x plus y2. So what you got now is P of x plus y1 is less than or equal to P of x plus y2. That's the quantity 1. Now you take the reverse way, that is P of x plus y2 you consider, you will get P of x plus y1 minus y1 plus y2. Again, we are having the triangle inequality, so this quantity is less than or equal to P of x plus y1 plus P of y2 minus y1. Again, the same reason, P of y2 minus y1 is 0. Since y2 belongs to E naught, y1 belongs to E naught, and E naught is a subspace. So y2 minus y1 also belongs to E naught. E naught is nothing but the kernel of P. That means P of y2 minus y1 is 0. So what you got is P of x plus y2 is less than or equal to P of x plus y1. Now from condition 1 and condition 2, we can conclude that P of x plus y1 is equal to P of x plus y2. Therefore, P of x plus y is independent of independent of y. Y belongs to E naught. Thus, P can be seen as a function on cosets. Because whatever is coming x plus y1, x plus y2, etc. does not change anything. If this y1, y2 belongs to a closed space x naught. So P can be seen as a function on cosets such that P of the class X is equal to P of X. And this does not depend the representative of the coset. That is, if you are taking P of X, the members of the form P of X plus some member from your X naught. But it is not at all, we have proved that it is not at all depending on the element from your X naught that we have written here. That is called the representative of the coset. Thus, a semi-norm P of x on E defines a norm on the quotient space E over E naught. So, once you consider the semi-norm, but now we have that semi-norm on a quotient space is becoming a norm. Okay, I think you can follow me. If you're having any doubt means you can ask. Any clarification further you need means again you can post your comments or post your doubt. Your doubts are always welcome. So here I am stopping today's session. Thank you for your patient listening. First of all, we will discuss the p-norm on function spaces. P-norm on function spaces. So consider C of AB. C of AB means a set of all continuous functions on closed level AB. In this set, we define a norm Fp is equal to integral a to b mod of f of x raised to p dx. Since when we are taking f of x, it is a real or complex valued function, that means defined on closed level AB. So we can use the mod. Now this is a continuous function and we are having the integral from a to b. So the norm is defined as norm of f with respect to p is integral a to b mod of f of x raised to p dx raised to 1 by p, which is finite. It should be finite. Then this is called the p norm. Now this norm is a this whatever we had defined is a norm. This normed space is denoted by Cp of AB. Set of all continuous function on AB with the norm P norm is called Cp of AB. Now again we will consider Rp of AB. That means set of all functions defined on closed level AB such that the p power of their absolute value is Riemann integrable. That is nothing but this quantity exists. Am I right? See, when you take the absolute value means you get mod f of x. Now take the pth power. That means mod f of x raised to p. And that value is Riemann integrable means this integral should exist. That is the above integral exists and that is finite. That we represent as Rp of something is went wrong. Okay. So the above integral exists and that is finite. Okay, Rp of AB or functions on AB such that the p power of their absolute value is Riemann integrable. Now that means the above integral exists. But we can note that this quantity is not a, yes, now we got. This quantity is not a norm anywhere. It's not a norm anywhere. But it is a semi-norm. So semi-norm means, the previous class we have studied that when you're having the norm condition, from the norm condition, if you avoid the condition that norm of x equal to 0 implies if and only if x equal to 0. That means since we can find piecewise continuous functions f not equal to 0 such that uh, norm of fp is equal to 0. So it is a semi-norm, not a norm. But we have seen that a quotient norm, sorry, when you're taking semi-norm on some quotient norm, it will become a norm. So we are considering quotient space. Now consider a quotient space of the above space with respect to the set of zeros of norm P. Note that this new space, note that this new space This new space consists of class of functions f and g. Now f1, f2 belongs to f means norm of f1 minus f2 with the p norm is equal to 0. That is, the Riemann integral of f1 minus f2 raised to p is 0. We had defined in that fashion. Norm of this means integral a to b, norm of f1 minus f2 raised to p, whole thing raised to 1 by p should be less than infinity, that we denote. Now this equal to 0 means we will get the integrand equal to 0. That means the Riemann integral of this quantity is 0. Now, we often think of the elements of such a space as functions by selecting a convenient representative of each coset. That means in your quotient space, we are having elements of this form. That is the equivalent class of f. Now from this equivalent class, we will select any one element. So let it be f1, f2 belongs to f means we will say that f1. So that f1 represents the entire equivalent class of this f1. So in such fashion, we represent each by cosets. Now passing to completeness or completion. In this session, what we are going to do is we will consider some spaces and check whether that is complete or not. Then further, what is the we will investigate what is the procedure for making a space to be complete. So definition 1.5.1, Cauchy sequence. So definition of Cauchy sequence. A sequence xn in X is called a Cauchy sequence if and only if for every epsilon greater than 0 there exists some n belongs to n such that norm of xn minus xm is less than epsilon for all n comma m greater than n. That is, norm of xn minus xm converges to 0 as n comma m tends to infinity. Now properties of Cauchy sequences. If xn is a Cauchy sequence, limit n tends to infinity, norm of xn exists. That is, no, consider mode of norm xn minus norm xm. Now this quantity is less than or equal to norm of xn minus x. Since it is Cauchy, this quantity is always less than epsilon for some nm greater than some natural number, which implies this quantity is less than epsilon. That is, when you consider norm of xn as a sequence, it is Cauchy sequence. Thus, it converges. The second property, xn is a bounded sequence. Since norm of xn is convergent, it should be bounded. That is, there exists m belongs to R such that norm of xn is less than or equal to m for all n belongs to n. For definition 1.5.2. A normed space X is called complete if and only if every Cauchy sequence. A normed space X is called complete if and only if every Cauchy sequence xn in X converges to an element X of the space. That means a space is said to be complete if you take whatever the Cauchy sequence possible from that space, and if that Cauchy sequences converges to some points in the space itself, then we will say that that space is complete. Now we are having some complete spaces, that is R with the usual metric or C with the usual norm or metric. Since a norm, from the norm we can go for a metric, this can be taken as metric spaces also, where is the usual norm. Now further, Rn, Mcn are complete spaces with the Euclidean norm. But Q with usual norm is not complete. Q with usual norm is not complete. This you have studied, so I am not going in detail of that. Definition 1.5.3. A complete normed space is called a Banach space. A complete normed space is called a Banach space. That means when you taking a normed space in that every Cauchy sequence converges and that converging point belongs to the space, then the space is called a Banach space. So how to check a given space is Banach or not? So how to check the completeness of a space means to check whether it is Banach or not. The first thing is that search for a first of all, consider an arbitrary Cauchy sequence in X. Now search for a hypothetical element X, which is expected to be the limit of Xn. That means, suppose we have got a Cauchy sequence, and we will assume that this is going to be the limit of that. Now, with that, we will check this X is an element of X or not. This is the second stage. Now prove that xn minus norm of xn minus x is converges to 0 as n tends to infinity. So this is the usual procedure for proving whether a space is complete or not. So in terms of normed space, when you are considering this means, we will use this word checking a given space is Banach or not. So here is one example. The space C of closed level AB is complete. That is, set of all continuous real valued or complex valued function defined on closed level AB. So we should consider a Cauchy sequence. So let Xn be a Cauchy sequence in C of closed level AB with supremum norm. Supremum norm means norm of Xn is equal to supremum of mod of Xn such that Xn belongs to E type. Then for every epsilon greater than 0, there is a natural number n of epsilon belongs to n such that supremum T belongs to closed level AB, norm of xn t minus xm of t is less than epsilon for all n comma m bigger than n of epsilon. Nothing but it follows from the Supremum norm. Xn is a Cauchy sequence. In the Supremum norm means you will get this condition. Therefore, for every t belongs to closed level AB, there exists a limit n tends to infinity, xn of t is equal to x of t. Cauchy sequence converges. So there exists a limit for such a sequence. Moreover, for a fixed n greater than n epsilon, now you take limit m tends to infinity. That means in this condition, when limit tends to infinity, we have already seen that this sequence converges to x of t. So this will become supremum t belongs to closed level AB mod of xn of t minus x of t, which is the xm of t will become x of t, which is less than or equal to epsilon. Now, we know that if a sequence of continuous function xn converges uniformly to a function x of t, then this function is continuous. That means this is nothing but a uniform convergence. So in this case, we can conclude that our x of t is continuous. Since each x and t we have taken from C of closed level AB, each x and t is continuous. Now we have shown that xn of t converges to x of t uniformly. Therefore, x of t is also continuous. If x of t is continuous means x of t belongs to C of closed level AB. That means our limit belongs to C of closed level AB belongs to our space. Therefore, the space we have considered is complete space. That is C of AB is complete. So we have got an example for Banach space as real number with usual norm, complex number with usual norm, any Euclidean space with Euclidean norm, and see here now C of closed level AB with supremum norm. Secondly, consider the space LP. Remembering this space, 1 less than or equal to p less than infinity is a complete normed space. Indeed, we should consider here one sequence xn. See here, I am writing m here, xm here. Don't get confused with that. This is depending only on n. So when you're taking the sequence xn means it is of the form xm1, xm2, xm3, xm4 like that sequence. Be a Cauchy sequence in the norm P. Now for epsilon greater than 0, since it is a Cauchy sequence, we are using that condition. That is for n comma k greater than n epsilon, we have sigma m equal to 1 to infinity mod of xm raised to n minus xmk raised to p is less than epsilon raised to p. Since we are having the norm as this thing raised to 1 by p. But if you're not using that 1 by p means we should write here epsilon raised to p. So this is our first condition. So I have written here. Now from this we can conclude that this quantity is less than summation of this quantity. So hence for n comma k greater than n epsilon we obtain. So this quantity is less than epsilon raised to p. So this quantity is less than epsilon. So norm of xmn minus xmk is less than epsilon. See, sequence this notation I am following from the text itself. Actually, you can take it as xmj or something like that. Which means that each sequence xmn n is a Cauchy sequence. When I am writing here n means the varying quantity is n. Is a Cauchy sequence, and by the completeness, see xm of n means we have the sequence in the real number or complex number. For the simplest notation, if I am writing xn, a sequence xn as can be taken as xnj type. So it is of xn of some j. If I writing means, see, this is my sequence. Now the fact is that each xnj will converges to some xj. This xnj will converges to xj. Xnj will converges to xj. Now your limit of xn should be of the form some x1, x2, x3. That means an infinitable time. Okay. Now each this converges to xj, where xj means it is a sequence in your real or complex number. So I have written as xmn of n is a Cauchy sequence, and by the completeness of real number, there exists a limit for this sequence, and that limit I am naming as xm. The limit of xmn as n tends to infinity. Then for every m belongs to n, sigma m equal to 1 to m mod of xm raised to p is same as limit of the sequence. Now this quantity is less than or equal to supremum of norm p of xn, which is less than some c and which is finite for some c greater than 0, since Cauchy sequences are bounded. Thus we got x is finite. Right? That means x belongs to L. Now from the condition 1, or condition A, this condition A, this was sigma m equal to 1 to infinity xm minus xm k raised to p is less than epsilon raised to p. From that, we obtain sigma m equal to 1 to m xm raised to m minus xm raised to k raised to p is less than epsilon raised to p for sufficiently large n and k. Now as k tends to infinity, what will happen? This sequence will converges to xm. So the summation will become sigma m equal to 1 to m norm of xm raised to n minus xm raised to k limit, it will converges to xm raised to p is less than or equal to epsilon raised to p. Now as m tends to infinity, we obtain sigma m equal to 1 to infinity mod of xm raised to n minus xm raised to p is less than or equal to epsilon raised to p, which means that this is nothing but, if you are having this raised to 1 by p, and this will become norm of xn minus x, since this is going to be the sequence xn. So norm of xn minus x with p norm is less than or equal to epsilon. Thus xn converges to x. Okay, I know that there may be some difficulty in understanding the notation in this example. That means since we are considering a sequence of this form, since I followed this, since in your textbook given this notation only. So uh, read carefully this example and do familiar with this notation. Xn means you are considering a sequence in your LP. Now from LP the sequence means coordinate wise. That means when you consider xn, it is of xn of t. That is x1 of t, x2 of t, x3 of t, like that. Now when you consider m of t, one coordinate here, that will already a sequence xn of t. Okay, so that sequence may converges to some real values. So the limit, when you consider limit of xn, means it is of the form. Again, it should be a infinite triple form. So it should be x1, comma, x2, comma, x3, comma, etc. type. Okay, with this, I'm concluding my today's class. Um, any doubt means you can ask. Okay, thank you for your patience. So, as note 1, L infinity equipped with a supremum norm is a Banach space. L infinity equipped with a supremum norm is a Banach space. So, we will prove it. The notes I have given you at the end of the notes the proof of this. That is, see here. The space L infinity equipped with the supremum norm is a Banach space. So proof, let Xn be a Cauchy sequence. To prove that it's a Banach space, we want to consider the Cauchy sequence and we want to prove that Cauchy sequence converges in L infinity. So we should consider the Cauchy sequence Xn in L infinity and take an epsilon greater than 0, and by the Cauchy sequence definition we will get for norm of xn minus xm less than epsilon for every n comma m greater than or equal to n naught. Now if n comma m greater than or equal to n naught and j equal to 1, 2, 3, we have xnj minus xmj is less than or equal to, that means supremum idea we are using. So this quantity is always less than or equal to supremum of this one, and that value is equal to, this means by definition it is norm of xn minus xm. Now this quantity is less than epsilon. You see, this is a sequence in your L infinity, but this is a sequence in your field. That means either it should be a real number or complex number. Now this follows that this sequence is a Cauchy sequence in your field, that is K or F. Now we know that the set of real numbers or complex numbers is going to be a complete field. So since F is complete or K is complete, there exists Xj, that is Cauchy sequence should have a limit, that is Xj, such that X and J converges to Xj. Now that means xn of 1, the sequence is xn of 1, that will converges to x of 1. Sequence x2 of xn of 2, that will converges to x2. Sequence xn of 3 converges to x3, like that. So with that convergence point, we can define a point x equal to x1, x2, etc. Then we will prove that this x belongs to L infinity. That is, we want to prove supremum j equal to 1, 2, 3, etc. Mod of xj is less than infinity, or this quantity is finite. See, for understanding sake, I'm saying you have got two sequences here. See, this sequences means it is contained in, it is a sequence in either real number or complex number. So this is in your real number. For the time being, I am taking this is a real sequence, and this one xn and xm, this all belongs to L infinity. Okay, this all belongs to L infinity. So here we are having two sequences. This is in R and this is in L infinity. You have taken a sequence in L infinity and we have proved that the corresponding sequence, that is if xn is there, means a sequence xn means that itself may be xn is sequence, means we will have xn of 1, xn of 2, xn of 3, like that. So that converges to xn. Okay, so this sequence is we have proved that is Cauchy sequence. So since R is complete, this Cauchy sequence will converges to R. That means it should have a limit. So that xj belongs to K such that x and j converges to xj. Now we will take this coordinate x1, xj's, that is x1, x2, x3, etc., and say that as a point x. And we will prove that this x belongs to L infinity. That is the limit of the sequence. Therefore, we want to prove supremum of j equal to 1, 2, 3, etc. Mod of xj is less than infinity. Now for n greater than or equal to n naught, we have xn j minus xn naught of j is less than epsilon. But this quantity we have another inequality. Mod of xn j minus mod of xn naught of j is less than or equal to xn j minus xn naught of j. Therefore, this quantity, we comparing these two, we will get this quantity is less than epsilon. That means take x and j alone. So mod of x and j is less than epsilon plus, see, epsilon plus this quantity. That is mod of x and naught of j for every n greater than or equal to n naught. That means x and j is bounded above. So x and j is bounded above means it should have a supremum. Let that supremum be k n naught. So let k n naught is equal to supremum of j equal to 1 to n x n naught of j. That means its supremum you are taking. Now you can take this as mod of xn of j is less than epsilon plus supremum of this, that is k n naught for every n greater than or equal to n naught. Now what does this follows? This follows since the sequence is bounded its limit, that is xi. So xi is less than epsilon plus k n naught for every I greater than j. Now take the maximum of these values, that is x1, x2, etc., xj, plus another quantity epsilon plus k n naught. So here I should take a comma, right? So here is comma, there's a mistake. Here comes comma. Okay. Thus, mod of xj is less than m. Conclude that mod of xj is less than m for every j equal to 1, 2, 3, etc. Therefore, its supremum is also less than or equal to this m. That is, supremum of xj is anyway it should be finite one. That implies your x belongs to L infinity. Now to prove that xn converges to x. We haven't proved that xn converges to x. Now we have seen xn and another point x, and we have proved that that point belongs to L infinity. Now we will prove that the sequence xn will converges to x. We have mod of xnj minus xmj is less than supremum, right? The supremum, with that supremum I can define a metric. That way I have written d infinity of xn comma xm. So that's equal to supremum of j equal to 1, 2, 3, etc. mod of xnj minus xm of j, and that is less than epsilon. Now keeping n greater than or equal to n naught and m tends to infinity, what we will have? N greater than or equal to n naught and m tends to infinity. If m tends to infinity, it will converges to xj, right? So keeping n greater than or equal to n naught and m tends to infinity, we get supremum of mod xnj minus xj is less than epsilon for every n greater than or equal to n naught. That is norm of. So this is true for every j with n greater than or equal to n naught means its supremum is satisfying. That is, supremum of this means nothing but your norm. That is, norm of xnj minus xj is less than epsilon for every n greater than or equal to n naught. That is, xn converges to x in L infinity. That is, L infinity is complete. So we proved that L infinity is complete. Next thing we will go for the first part of our class, that is L infinity equipped with the supremum norm is a Banach space that we have proved. Now to prove C1 and C0 are also complete, we need not prove it as a whole, that is take Cauchy sequence and prove that it converges and that convergent point belongs to this. No need of that. So it is sufficient to show that they are closed subspaces of L infinity. That means we want to show that C1 and C0 are closed in L infinity. So once you prove that, we have proved that C and C0 are closed subspaces. Next definition. Let E and F be normed spaces. We say that a linear map T from E to F is an isometry into if and only if. See, up to now in some textbook it is given only isometry, but in your textbook is given as isometry into. So it is said to be an isometry into if and only if norm of Tx in F is equal to norm of x in E for all x belongs to E. That means you are having a set E, this is your E and this is your F. Now we are having a map T. So this T is said to be a isometry into if you take a element over here. Now find its, this is your E and yes, I should write like this, E, and this is your F. So you can take an element X on E, see this X. Now I can find its image as Tx. So here I am having my element Tx. Now if two element is there, means these two are normed spaces. So you can go for the norm of this. Now when you find norm of x, you are getting the, it is equal to norm of Tx. Then we will say that this T is an isometry into. Now we will prove the core of our chapter, that is, if a normed space is given, it exists a extension of that as a complete normed space. Okay, so completion theorem. Let E be a normed linear space, there exists a complete normed space E hat and a linear operator T from E to E hat such that norm of Tx is equal to norm x. That means it's a isometry into, and image of T, that is Te, enter image of T and E under T, that is Te, is dense set in E hat. That is, we want to prove that Te closure is equal to E hat. So what this theorem is saying is that if such a condition is existing, we will call the space E hat the completion of E. Then we will call the space E hat the completion of E. We are having a normed space E and a complete normed space E hat and a linear operator T from E to E hat such that it's an isometry and its image set is dense in E hat. Then we will say that E hat is the completion of E. So proof of this. Let epsilon, capital Epsilon, be the linear space of all Cauchy sequences. So you can take that to be as epsilon or E itself, script E. That's enough, I think, because we are using epsilon for Cauchy sequence convergence ideas and all. So let it be script E. So script E be the linear space of all Cauchy sequences. X bar is equal to xi, where xi belongs to E. It's a sequence notation in E. Introduce a semi-norm. What was a semi-norm? A semi-norm is a semi-norm we get from avoiding the condition norm of x equal to 0 if and only if x equal to 0. When you delete that condition from your norm definition, you will get a semi-norm. So introduce a semi-norm in the space script E by p of x bar equal to limit I tends to infinity norm of xi. Limit I tends to infinity norm of xi, where x bar is equal to xi is a Cauchy sequence, where x bar is equal to xi is a Cauchy sequence. Then by property of Cauchy sequence, the limit always exists. Okay, what you are considered is, first you consider script E as a linear space of all Cauchy sequences in E, and we have introduced a semi-norm in the space E by p of x star is equal to limit I tends to infinity norm of xi. Now this exists since it's a Cauchy sequence. Then property of Cauchy sequence, we have studied that norm is always exist. Now take its kernel, right? Now define n equal to x bar such that p of x bar is equal to 0. Now this n is a subspace of all sequences which converges to 0. Now we can define a norm p on the quotient space script t by n. Okay, previous class you have seen that when you're having a semi-norm and you are defining the semi-norm to be in a quotient space, that will result in norm. So here too we are having a quotient space script e by n, and you define this semi-norm on this space, you will get a norm. Now take this quotient space as E hat. So what we want to prove now? Now we want to prove that from E to E hat there exists an isometry into and image of that isometry TE closure is equal to E hat. Okay. Now P of x bar is equal to limit I tends to infinity norm of xi for any representative, because when you're taking an element over here means it will be a bracket of xi of this form. Last class we have discussed that. It should be of the form some xi of this type. We will say that cosets. So any element of this is of the form, if this I am writing means this is of the form some xi plus, so I should write xi plus n form, because it's a coset, right? Element in quotient space. So P of x bar I have denoted as limit I tends to infinity norm of xi for any representative. Representative means if I am taking this as my coset, now xi is my representative. Any representative x bar of an equivalence class x bar, where x bar equal to, yes, I have written that. Now define the operator t from E to E cat is defined by tx is equal to the coset x bar. So you have defined coset x bar, where x bar is the constant sequence xxxxx. Okay. Now constant sequence is always a Cauchy sequence. So it is defined. Since E hat is equal to script E by n, we will again have elements of the form some x plus n type. Now this is evidently defined. Now to prove the theorem, we should prove TE is dense in E hat and E hat is a complete space. Now we will prove the first part. Let x bar equal to xn belongs to script t for all epsilon greater than 0. Now there exists n belongs to n such that norm of xn minus xm is less than epsilon for m greater than n greater than or equal to n. This follows from Cauchy sequence idea. Now define xn bar belongs to script e by xn bar equal to the constant sequence xn, 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 etc. Now by our definition, t of xn is the coset xn bar. Now find the distance between xn bar and to xn. That is, we'll say that the coset x bar to xn bar. That is p of coset x bar minus coset xn bar. By definition, that's equal to p of x bar minus xn bar. Now p of x bar minus xn bar is less than or equal to epsilon. Why? Since xn bar means we are having xn, 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 etc. Okay. Now x bar means we are having this constant sequence x, 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 etc. Right? And we have found that xn minus xn bar. See, xn bar is equal to x, 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 etc. And here we are taking this quantity x bar minus xn bar. So it should be always less than or equal to epsilon. Thus, every x bar belongs to E cap is approximable by elements of TE. Can you follow? We have taken x bar and txn. Now we have found that the distance between xn bar and x, okay, is very less. That means any element of E cap, that is coset x bar, can be approximable by elements of TE. Now for a Cauchy sequence x bar equal to xn, the sequence txn of constant sequences converges to x bar. So we have proved that. The first part. What was the first part? What was the first part? What we want to prove? Let's say condition A. Condition A says that TE is dense in E hat. So we have proved that TE is dense in E hat. Now to prove E hat is a complete space, we will use the same idea here. Now consider a Cauchy sequence. See here the notation is x bar n. Generally we will write x bar of n over lower side, but in this textbook it is given as in the upper side. So I am following the same thing. So consider the Cauchy sequence x bar n in E hat. We have that p of x bar n minus coset x bar n minus x bar m. That's equal to p of representative you are taking. So x bar n minus x bar m. This quantity converges to 0 as n comma m tends to infinity. You used only the Cauchy sequence idea. Now take an epsilon n greater than 0 and converging to 0. That means we are having a sequence of positive terms which converges to 0. That means the 1 by n you can take. So, and xn belongs to E such that p of x bar n minus t of xn is less than epsilon n. We have to prove TE is dense in E hat. Then you consider x bar naught, that is sequence xn is a Cauchy sequence in E. Now find whether it's Cauchy or not. So take norm of xn minus xn. That is by definition p of xn means t of xn. This means t of xn. So p of txm minus txm, that is less than or equal to, you can introduce here x bar n, and here see x bar n and x bar n. Similarly x bar m and x bar m. Now using triangle inequality, we will get this quantity is less than or equal to p of txn minus x bar n plus p of x bar n minus x bar m plus p of x bar m minus t of xm. So this quantity we can take, this all is less than epsilon by 3, epsilon by 3, epsilon by 3. So you get this quantity is less than epsilon for every n comma m greater than some quantity. Okay, so generally we can say that this norm converges to 0 as n comma m tends to infinity. Therefore, x bar 0 is equal to xn belongs to our script E, and further limit of for x bar 0 is equal to limit of x bar n. Now since p of x bar 0 minus x bar n, that's equal to, again you can write p of x bar n minus x bar of 0. Since the symmetry relation which is less than or equal to p of, see here we have introduced txn. So we will get by using triangle inequality which is less than or equal to p of x bar n minus t of xn plus p of t of xn minus x bar 0. That means this quantity converges to 0 as n tends to infinity. So we have proved that Tx bar is dense in, or T E is dense in E hat. That's the theorem. Okay, I'm closing today's session. Thank you for your patient listening. If you're having doubt means, please do find some time to ask me about the doubt. Either you can post it in your classroom or post it in the WhatsApp group. Okay, thank you.